Hello everyone, my name is Ruoyang. Talk about GridSE towards practical secure geographical search via Prefix Symmetric searchable encryption. This is a joint work with Jiarui and Shucheng from Stevens Institute of Technology, AISEC Lab. Let me start with a real-world scenario. An app that provides geographic search service runs on sensitive data. A lot of GIS apps in our daily life, such as Instagram or Facebook. These GIS apps usually need to collect personal information from users, like users' real-time locations. While data stored in the GIS servers, which are usually hosted to cloud, this will trigger privacy concerns. The security model here is clear: a client for a GIS app and a server for cloud. Considering a case if a client directly puts its data into cloud, it is very risky and easy to be attacked. So in an ideal state, geographical data needs protection, better to be encrypted, and can be faster searched. However, our concern is the compatibility with discrete global grid systems. Existing GIS apps have been deeply rooted in a so-called DGGS system, which is an encoding system for structuring and indexing two-dimensional spatial data or higher dimensions to a string. DGGS has different variants for encoding locations and finally outputs a string. Includes GeoHash, Google S2, or Uber H3. Let me use a query case here, for example. A tourist who asks best places to visit in New Jersey, and New Jersey will be encoded to DR5R in a DGGS, and the returned search result might be Statue of Liberty, and this place will be encoded to DR5R7. So if we observe these two strings, we'll find that this is in essence a prefix search problem. So a secure geographic search app, SGS app, needs a secure DGGS, and that essentially needs a secure prefix search. To build a practical SGS system is not easy. One outstanding challenge is to assure near latency-free instant search responses and to be compatible with the mainstream DGGS systems. Since DGGS requires prefix search, the solution needs to be searchable encryption for prefix. In addition, it needs to support dynamic search, especially considering insertion or deletions of GIS databases. However, this dynamic updates triggers privacy concerns. We need to guarantee this protection, in particular forward and backward privacy. Forward privacy means newly added data cannot be linked to previous queries, and backward privacy means a query cannot be linked to previously deleted one. If we look at the previous works on dynamic SSE, we will find a set of these works focus on the whole keyword search rather than supporting prefix search. And another line of substring search, secure substring search, exhibit trade-offs between efficiency, update, security, and false positive rate. However, this rapidly constructing SGS scheme with existing crypto primitives is very difficult. Let me show our design here. We first designed SP2E, a new cryptographic primitive, to evaluate whether a keyword contains a prefix. We give an example here for how SP2E worked. Now, a place of DR5R7 we showed previously in server needs to be searched. We map each character to crypto hash functions in a hierarchy structure and use a pseudo-random value to mask it. Finally, XORing these values, we can get a cipher here. To make this cipher searchable, we need a token generated from the client who holds the code DR5R prefix. We also map each character to a crypto hash function and mask it with a fresh pseudo-random value. But this is not enough for search, right? we need to introduce some definiteness here. So we simply substitute a portion of this fresh value, fresh pseudorandom value with the same portion of the pseudorandom in server's cipher. Finally, just by a single XOR operation between the token and the cipher, we will find the 0 bits will expose in the specific positions. That's what we want. Via the exposed 0 bits, we can identify the keywords what we're looking for with the queried prefix. Next, what we need to do is extending SP2E to forward and backward privacy. To prevent updates from leaking information, we need to encrypt triplets of keyword, file ID, and operations of deletion or addition. And we organize these triplets by a dictionary map. Keywords are put in the key area and encrypted by SP2E such that it can be searched by prefix. And the triplets with the same keywords or at the value area in a list format. Then we need to encrypt these triplets for guaranteeing dynamic secure, which means at least a update counter should be hidden. However, only hiding update counter for encrypting triplets will produce the same ciphers here, not enough for prefix, not enough for forward and backward privacy. Our design achieves this privacy standard with the help of only an extra single parameter, the dictionary sequence of address, the sequence of key. We are integrating this sequence information to encrypt the triplets. The server cannot distinguish triplets between insertion and deletion. Except for extending SP2E to dynamic security, we also provide a generic framework for transforming a dynamic SSE to a dynamic prefix SSE. Key points are simple. Just need to follow the two rules in GridSE. The first is to keep the basic setting and processing flows of GridSE, which means the secret keys storage and arrangement between the clients and the server. And the second is to follow the dictionary structure, which means key on prefix search and value on other SSE methods. Then it is very likely to make generic dynamic SSE for keyword to work as a prefix dynamic prefix SSE. We implement GridSE over real datasets. By processing the global location dataset, we obtain 60,000 distinct users within California. And we tested various database sizes. We use database sizes from 1,000 to 1 million, and the query size we controlled within 10 to 10,000, spanning from 100 kilometers to 100 square meters to 100 square kilometers. And we also tested different DGGS methods like GeoHash, Google S2, and Uber H3. For deletions, we deleted random 10% of the results that matches the queried prefix. If you look at the evaluation of our design, you will find the GridSE shows a very efficient performance for real settings of geographic search environment. With a database of 1 million files and a result of 100, a search over self-tests, including decryptions, requires only 20 milliseconds. And the deletion percentage impact the GridSE performance very slightly. No notable variations in search time changes for fixed database size of 1 million and fixed result size of 10,000. GridSE shows advantage also in communication and update. The communication cost grows linearly with the result size, but is independent with the database size. That is good for practical usage. And the result size growing is caused only by the larger query range. For updates, it is quite sensitive. Both the update time and the communication size are constant. 5 microseconds for time and 8 bytes for size for single update. So in Ruoyang, we propose GridSE, a dynamic prefix assay scan, which can support fast, secure geographic search with updates and support backward and forward privacy. To construct it, we designed a new crypto primitive SP2E for realizing prefix search. For performance, we did a lot of comparisons with SOTA. It shows that GridSE reaches 150 to 5,000 times the speed up in search time and the 99 saving in communication cost than SOTA. And we also compare it with the plain text search. It is interesting. GridSE only introduces more 1.4 communication cost and 0.9 more communication overhead. By leveraging the lightweight crypto operations, GridSE built a top SP2E, introduces almost the constant cost within a given geographical area, and is thus highly scalable. That's it. So if you have questions, just feel free to touch.